Hello friends, here in this video we will see a problem on bushpin type flexible coupling. For that purpose, here I have a diagram of a bushpin type flexible coupling and here I have a question. First, I'll read what is given here. Design a bushpin type of flexible coupling to connect a pump shaft to a motor shaft transmitting 32 kilowatts at 960 rpm. The overall torque is 20% more than mean torque. The material properties are as follows. Allowable shear and crushing stress for shaft and key material is 40 megapascal and 80 megapascal respectively. Allowable shear stress for cast iron is 15 megapascal. Allowable bearing pressure for rubber bush is 0.8 Newton per mm square. Material for pin, shaft and key is same. Now this is the problem we have on bushpin type of flexible coupling. As it is in this diagram, bushpin type of flexible coupling, it has two halves. One is called as the left half, other is called as the right half. From the diagram it is very much clear that if I look at this section, this is called as the pin. This pin is having some different kind of an area. At first it is an enlarged portion and then the diameter goes on reducing. So these are called as pin and it has bush, that is why the name of the coupling is bushpin type of flexible coupling, and it is used wherein the coupling has to absorb shocks. If there is shock loading, then we go for bushpin type of flexible coupling. Here both the shafts, they are connected. At first the shaft in the left half is connected to the hub with the help of key. Shaft in the right half, that is connected to the hub with the help of another key. Next, here we can say that small d, it is the diameter of shaft. Capital D, it is the diameter of hub, which is taken as 2 times of diameter of shaft. D1 is the pitch circle diameter for the bolts. D2 is the outer diameter of the flange. L is the length of flange, or we can say the thickness of flange. Now this pin, which has different area, different diameters. On one side the diameter is D1 in the right hand side. On left hand side the diameter is D2. So now, as we have understood the bushpin type of flexible coupling, whatever is given in this problem, that I will write in the form of data. In data, at first I will have to write the type of coupling. It is given that we have bushpin type of flexible coupling. Now I'll read the question. Design a bushpin type of flexible coupling to connect a pump shaft to a motor shaft transmitting 32 kilowatts at 960 rpm. So power and speed are given. Power P is equal to 32 kilowatts. It is 32 into 10 raised to 3 watts. Speed is 960 rpm. Next, the overall torque is 20% more than the mean torque. So it can be written that overall torque is nothing but maximum torque, that is equal to 20% more than mean torque. So it means T max is equal to 1.2 times of T mean. Next, they have given us some material properties for allowable shear and crushing stress for shaft and key material. That is, I'll write down for shaft and key, they have given us allowable shear stress tau is equal to 40 Newton per mm square, and crushing stress is equal to 80 Newton per mm square. Next, allowable shear stress for cast iron is 15 megapascal. So cast iron is the material which is used for flange. So for flange, as the material is cast iron, tau is given as 15 Newton per mm square. Next, allowable bearing pressure for rubber bush. So for rubber bush, the allowable bearing pressure is 0.8 Newton per mm square, that is P suffix B, the bearing pressure which is given, bearing pressure for rubber bush. Last, material for pin, shaft and key is same. So pin, shaft and key are of same material. Now this is the question which we have. It is given that the design a bushpin type flexible coupling to connect pump shaft to motor shaft. So here I can say that let the right hand side shaft be the pump shaft and the left hand side portion or this shaft be motor shaft. So with all these data written, pump shaft and motor shaft, that is understood, let us start to get the design. So into the solution part, I'll say that step number 1, it is design of shaft. Now, since we know that the shaft is continuously rotating, so it would be subjected to torsional shear stress. So I'll say that since power transmitted by shaft P is equal to 2 pi nt upon 60. So therefore T will be equal to P into 60 upon 2 pi n. Here I'll put the values. Power, it was 32 into 10 raised to 3 and speed 960. So now here I'll get the value of torque and my answer is, it comes out to be 318.3 Newton meter. Now this torque which we are getting from the power formula, that would be called as mean torque. In the question they have given the relation between maximum and mean torque, and I'll say that since T max, the overall maximum torque, is 1.2 times of T mean, since it is 20% more. So here I have 1.2 into 318.3. So therefore T max, my answer is 382 Newton meter, or I can say it is 382 into 10 raised to 3 Newton millimeters. So after getting the torque, we can easily design the shaft. I can say that since torque transmitted by the shaft, so after getting the value of maximum torque, I'll say that torque transmitted by the shaft T max, it can be written as pi by 16 d cube into tau, where tau is the shear stress for the shaft material. and D is the diameter of shaft. Here I am assuming, since nothing is given about the shaft, so I'll say that it is a solid shaft. I'll go on putting the values. Therefore, T max, it was 382 into 10 raised to 3 Newton mm. Tau, shear stress for shaft, it is given as 40. So throughout, if I calculate, I will get my answer first of D cube, that will be 48.6 into 10 raised to 3. After getting the answer of D cube, I'll get D by taking the cube root of this, and it comes out to be 36.5, which we can make it as 40 mm. So here we get the diameter of shaft in step number 1. Next, in step number 2, here I will design the design of pin. Now, in case of bush pin type flexible coupling, the pin is of a different shape. It is something like this. I'll draw the diagram and explain. Now, the pin used here looks like this. This is the threaded portion, and the left portion, it is, we can say, a solid member, not a threaded section. Now, the diameter here of this threaded portion, that would be D1. Next, the diameter of the enlarged portion, this would be D2. So I'll say that since, or we can say let D1 be equal to diameter of pin, and for that we have the relation D1 is equal to 0.5 times of diameter of shaft upon root of n, where n is equal to number of pins. Here I'll assume the number of pins as 6. So this is the empirical formula which I have, out of which I can calculate D1. So therefore D1 becomes 0.5 into D, diameter of shaft, that was 40 divided by root of 6. So my answer is 8.2 mm. Now this 8.2 mm is a very small diameter, and if we are using such a small diameter on one side, it may result in bending or even twisting failure of this small section. So I'll say that therefore, to increase the load carrying capacity, D1 is equal to 20 mm. I am assuming a higher value, higher than 8.2. So if D1 is 20, this enlarged portion, therefore D2, it will be equal to D1 plus 4 mm. Again, this is by empirical relation. Next, therefore D2 becomes 20 plus 4, 24 mm. Now after getting D4 or D2, as we can see in the diagram of bush pin type coupling, after D2 there is a brass bush of 2 mm thickness, and then there is rubber bush of 6 mm thickness. So now I can calculate the overall diameter of the bush or hole in this left flange. I'll say that therefore overall diameter of bush, that will be, I'll denote it by D3 is equal to D2 plus 2 into 2 plus 2 into 6. What are these values? I'll say that taking 2 mm thick brass bush and 6 mm thick rubber bush. So 6 mm indicates the thickness of rubber bush, 2 mm thickness of brass bush. So therefore D3 comes out to be 40 mm. Since D2 is 24, so 24 plus 4, that is 28, and in that 12 the answer is 40 mm. Now once we have designed this pin, the next step is we can get this diameter D1, which is called as the pitch circle diameter. I'll say that since pitch circle diameter, which is D1, it is given by the formula D1 is equal to 2D plus it is D2 plus 2 into 6. This is the again empirical relation which we are using. I'll write down this formula as come by empirical relation. So here therefore D1 is equal to 2 into D is 40 plus this is actually 2D plus D3. D3 is the overall diameter which is 40 plus 12. I calculate this, my answer is 132 mm. So this is the pitch circle diameter which I am getting. Now after this I can say that checking of pins under shear. Now when we are checking the pins under shear, we can say that first I'll find the load acting on this pin, then I will divide load by the area. The load which is acting here, that would be called as bearing load. So bearing load on pins W, that is equal to the bearing area, which is nothing but D2 into L multiplied by bearing pressure. So here W is equal to, that is actually D3, so it is 40 into length is what we don't have. Bearing pressure is given in the problem. The bearing pressure, it is 0.8, so into 0.8. Finally this comes out to be W is equal to 32 into L, unit will be Newton. Next I'll say that therefore after this the torque transmitted is given by, since torque transmitted is given by T max is equal to the load on the pin, that is W, multiplied by number of pins into D1 by 2. So therefore I'll put the values. T max, it was 382 into 10 raised to 3. W is 32 into L. N we have assumed as 6 number of pins. The diameter of fifth circle, that is 132 D1. So from this I'll get my answer of L, and that is 30.1. I'll round it off to 32 mm. So this is the length of pin. So now for checking it for shear stress, I'll say that therefore shear stress tau is equal to load upon cross sectional area. Load, we know it is 32 into L. L is again 32. because W was 32 into L. Area is pi by 4 into D1 square, and D1 was 20. So from this I will get the answer of shear stress, that is 3.26 Newton per mm square. Now this value is less than shear stress for pin which is given. That was shear stress for the pin should be taken as same as shaft and key because they are of same material. So it is 40 and R value is less than 40. So we can say that this pin is safe under shear. Next, after designing the shaft, designing the pin, now I'll say that therefore step number 3, it is the design of flange. In this design of flange, I'll say that first of all, let TF be the thickness of flange, and that is given by the relation, it is 0.5 times of the diameter of shaft. So 0.5 of 40, TF comes out to be 20 mm thickness of flange. Now I'll say that therefore outer diameter of flange, it is the greatest diameter. In the diagram, if I can show this here, the outer diameter is denoted by capital D2. So I'll write D2 will be equal to 4 times of diameter of shaft, that is 4 into 40. Hence D2 comes out to be 160 mm. Now after this, I'll say that we will check this flange in shear, because what may happen that when the shaft is rotating, there are chances that this at the hub, this flange would break like this. It can shear it off. It can break at the hub. So that is called as shearing of flange. So I'll say that considering flange under shear, since shearing area capital A, that will be equal to pi into D, that is the diameter of hub, because flange is breaking at the hub, so it is pi D multiplied by the length of hub, it is multiplied by the thickness of flange actually, by D into, because this flange thickness would be sheared off, so into the thickness of flange, that is the shearing area. So therefore after this I can say that torque transmitted by flange is given by, now as I have written torque transmitted by the flange is given by, at the flange it means it is at the junction of hub and flange. So that torque is given by, I have written the formula here. Now I am putting the values. Here I have pi, this capital D, it was 80 into thickness of flange, that was 20. Shear stress is what we have to find out. D is again 80. So from this if I calculate, I'll get my answer of tau, that is 1.9 Newton per mm square. Now this value of shear stress, I can say it is less than the shear stress permissible given for the flange, and that permissible value was 15 Newton per mm square. Hence I can say that, hence the flange is safe under shear. So in this video we have seen the design of bushpin type flexible coupling, starting with the shaft, then we have designed the bushpin, and then we have designed this flange. And I think everything is understood here.